in the previous part of the course is that there are four parameters that describe the transformer. So what are the four parameters? R naught, X naught, R01 and X01. So this is the resistance representing the iron losses. This is the reactance representing the magnetizing current. This is the total resistance referred to the primary. This is the total reactance referred to the primary. So you have seen this before. So these four, what all we can do? So we can calculate losses, we can calculate regulation, voltage regulation that is, and we can calculate efficiency, so etc. for different loads. So that is the advantage. So now the question now comes is how to determine these parameters. How to determine above parameters. So this is the question. So the two simple tests. So one is the open circuit test, or it is called OC test. This will give me R naught and X naught values. Another is the short circuit test. This will give me R naught 1 and X naught 1 values. So just by doing these two tests, I can find out uh, each test will give me two values. So I'll show you how we will do that. So first let us discuss the open circuit test. So OC test. So open circuit test, what we do is we take the transformer. So here is our transformer, and we take the low voltage side of the transformer, and the high voltage side, the winding of the high voltage side is kept open circuited. So that means naturally this current will be zero. So whereas on this side, what I'll do is, this is the winding. So first I'll keep an ammeter immediately here, and then there is a wattmeter. So wattmeter will have two connections. One is the current coil, other is the pressure coil, and then finally I'll have a voltmeter. And here I'll give a supply. So here I'll have to apply rated voltage. So it is very easy to analyze this. See, whatever current here flows, that will be the no load current, because I2 is 0, I2 dash will also be 0. So therefore I1 will be nothing but I0. You know that from the previous studies. So I1 is nothing but I0, and not only I1, first I am measuring the voltage. So this voltmeter will tell me whether I am applying rated voltage or not. So sometimes you might, we don't know what voltage you're applying, so we can measure that. This wattmeter will tell how much is the input power, so P naught, and this ammeter will tell how much is the current I naught. So, so with this value, so here here this voltmeter will give me V naught reading. Now given these three values, how to determine R naught and X naught? So just you can see as it is. See what happens if I simply see voltage and current I know. So what is the impedance? So in fact, even before I calculate the impedance, see I know the wattmeter P naught power. So I naught square R naught is nothing but P naught. So therefore, I can directly find R naught, that is nothing but P naught divided by I naught square. The simple power law. This is the wattmeter reading. This is the ammeter reading. From that, I can know what is the R naught. And once I know R naught, so how to get X naught? So let's see. See, I can get the total impedance. So what is Z naught? Z naught is nothing but V naught by I naught. And once I know the impedance, so now I can find out the X naught. It is nothing but Z naught square minus R naught under root. So just using these formulas, I can find out. So two formulas I have to use to, actually this is only one formula, this one, and the second formula I have to use this. So R naught, Z naught and X naught I can find out. That's it. This is the objective. The objective of the OC test is to find out R naught and X naught, and then we'll do that. So here one question that remains is that the secondary side is open circuited, which is usually the HV side is open circuited, LV side is metered, and we do the experiment here. We can do the opposite also. We can keep the LV open and HV also. We can do the this whole experiment and we'll get the same values. But then just think about it. Why we should do it in the LV side? So I leave it you to think about it. Now another thing that comes up here is this losses which are there. So this is again something kind of interesting. So this topic, let's call it separation of iron losses. So what happens here is we have this total iron P naught, which is total iron losses. So by the way, why this experiment is giving iron losses only? First of all, the rated voltage, this since this I2 is open, there is no copper loss in this winding, and here also since I0 is only 2 to 3% of the actual full load current, the copper loss due to I0 is very negligible. So therefore, whatever loss happens, that is core loss itself. So that is the reason for that. Okay. Now, typically it is observed experimentally that iron. We know that iron losses is nothing but hysteresis losses plus eddy current losses. So what is hysteresis loss? Because of the magnetization, demagnetization, reverse magnetization, so on that happens in the core of a transformer, the core molecules get realigned all the time, and because of that motion, there will be heat in the core. That is the hysteresis loss because of the reversal of magnetism. Similarly, what is eddy current loss? Because of the change of flux, there will be current induced in the transformer core also, because transformer core also electrically it can carry the power, but although it is not it's completely isolated, not connected to anything, but there will be some circulating currents flowing in the transformer core that results in heating again. So that is called eddy losses. Now it is found that, so let's call this Wi and let's call this WH and let's call this WE. It is found that experimentally WH is equal to some coefficient P into B max to the power of 1.6 into F. So the hysteresis loss is proportional to frequency. Hysteresis loss is proportional to 1.6 to the power, like maximum flux density raised to the power 1.6. Hysteresis loss is proportional to that. This is like an experimental result that is found. Similarly, eddy current losses is proportional to some constant Q multiplied by B max square and multiplied by F square. So it is noted that the eddy current loss is proportional to the square of the frequency. So now if I keep the B max constant for both, so actually this P and Q are constant themselves, but if I keep even B max constant in both in the regular operation, so I can combine this entire thing into constant. So I can say A into F and B into F square. So in other words, hysteresis loss at a constant flux density proportional to frequency, eddy current loss at a constant flux density proportional to frequency square. This A and B are constants which can be determined by testing again. So how to determine these two? So we'll do the above experiment, the open circuit test to be carried out at two different frequencies. So then from the test result we can separate WH and WE. Anyway, we'll solve some example problem based on this. At the time you can really get the feel how it is done. So so this is about concept of separation of iron losses. So first of all, determination of iron losses we can do by doing OC test. So full load supply rated voltage will be applied. So whatever iron losses are there, and you also know that the flux in the core is constant, whether it is open circuited or short circuited or no load or full load or half load, whatever, the flux in the core is always constant. So therefore, this losses, the copper losses, sorry, the core losses are always constant and they are always there in the transformer. So that we can determine by this open circuit test. And for doing separation of losses, we have to do two different tests here. That means two different frequencies. We'll solve an example problem on this so that you will be clear about that concept also. So that is about open circuit test. Let's go to the next test, that is short circuit test. So now we come to the short circuit test. So this short circuit test is also called as impedance test. So why it is called impedance test? Nothing but because we are doing this to know the impedance values. So R01 and X01 we can determine. Or you can also say R02 or X02. So it depends on which side you are doing the experiment. So you know how to transfer between R01. If you know R02, you can find R01 and so on. So equivalent resistance refer to one of the sides of the transformer we can determine using the short circuit test. So the circuit diagram is exactly same. So I can actually go back and then copy the circuit diagram from here. So let me select this region completely. Yeah. So some unwanted parts I'll delete. So here I don't supply rated voltage, actually supply reduced voltage. And here actually this part is different. And this part is different. So this part I'll delete. So I think I have everything ready. Alright. So because it's a short circuit test, what we do is short circuit the low voltage side and the meters are connected in the high voltage side. So compared to the open circuit test, the short circuit test is done on the other side. The meters are kept in high voltage and the short circuit is done on the low voltage side. Again, you can do it reverse also, no problem. It's ultimately it's the same thing, it will work. But then it is more convenient and the results are more accurate. The values are more accurate if you do this way. And I will also ask you to think about it, why it is done like that. And then because this side is short circuited, it should be dangerous to apply full voltage here. So reduced voltage. So in fact, we start with 0 volts and then gradually increase this voltage such that, uh, of course, I can also connect an ammeter here and measure the current here, or this ammeter also shows the current. So this, let us call it ISC, the short circuit current. I know what is the short circuit current in the primary by knowing the ratings of the transformer. So I gradually increase this voltage such that I meet this criteria that short circuit current is flowing in the HV side. Similarly, it will be observed that when short circuit current is flowing in HV side, short circuit current will also be flowing in the LV side. We can verify that by connecting ammeter here. Otherwise also it is fine. Then the wattmeter power, let's call it PSC. That means power during short circuit, and then let's call this VSC, voltage during short. So VSC is typically 5 to 10%, 5 to 10% of the rated voltage. So under this reduced voltage, I am sending. So now the argument is that because the voltage is less, the flux is less, and because the flux is less, the iron loss is negligible actually. So even under normal conditions, full voltage, rated voltage, the no, that I naught current is anyway 1 to 2% of the full load current. But then with reduced voltage, the effect is even more severe. So there is no iron loss in the core. But then the full current is flowing through the windings. Therefore, there will be I square R losses in both the windings. So therefore, everything, whatever this power meter is reading, that power meter, whatever it is reading, is the full load copper loss of the transformer. Thus we get the copper loss. And then if I know the full load copper loss, then what is, see, R01, assuming this HV side is the primary side, R01 into ISC square is nothing but PSC. So PSC is measured, ISC is measured. So therefore, I can find R01 is nothing but PSC divided by ISC square. So just by this calculation, I know what is R01. How to find X01? Simply, again you see, here you see, what do we have? So we have VSC, ISC. So Z01 will be VSC divided by ISC. So therefore, from this I can find the X01. That will be Z01 square minus R01 square under root. This way. So that's it. So we are taking three readings, 1, 2, 3. From these three readings, we are finding these two parameters, R01 and X01. By the way, in the above open circuit test, I forgot to mention one more thing. We can also find the cos phi, power factor. So no load power factor. So how to find cos phi naught? So P naught is nothing but V naught, I naught, cos of phi naught. So I am measuring power, I am measuring voltage, I am measuring current. From these three measurements, I can find out the cos phi naught. So once I have the cos phi naught, I can find out R and I can find out X. That is also another anyway known thing. I just wanted to add. So that's it. By just doing these two simple tests, even if it's a very large transformer, also it is fine. So what are the advantages? So advantages of this open circuit and short circuit test is, so what are the advantages? So advantages are, first is I have both are economical, OC and SC test. So economical to do, because at any time these are operating on no load actually. So because they are operating on no load. Open circuit there is no load, short circuit also no need to load. So it is good and it is convenient, and it is because we are just taking three readings and we're getting two parameters in one and all. So it can be done in a much faster way. So with this, let's the theory about short circuit test and open circuit test is over. So let's look at some example problems to solve. Okay. Now let's look at this example problem. This is example number 31. And here the objective, if you see, obtain the equivalent circuit of a 200 by 400 volt 50 hertz transformer with the following two test results. So as I said, these tests are very convenient, very simple, and then each test is just three readings are given, and three readings for short circuit test and three readings for open circuit test, and then we have this thing. So let's get started and let's work on it. So first thing you notice, let's just verify this is 200 and this is 220. It's supposed to be the same. So I think I made a mistake in noting down. So this is, that's fine, not a problem. Here we'll make this as 220. So if some of you might have attempted, this is 220 by 400 volts. So the test, always note that the test has to be done the open circuit test has to be done at the rated voltage, and the metering is done on the low voltage side and the high voltage side is kept open. So anyway, let's get started. So my P open circuit is nothing but 70 watts. So therefore, so I can write V open circuit is 220 volts and I open circuit, it's actually I naught, is 0.7 amperes. So first step is to find cos phi naught. So POC is nothing but IOC VOC cos of phi naught. So from this, cos of phi naught will be nothing but 70 divided by 220 into 0.7. So let's use calculator to do that. 70 divided by 0.7 multiplied by 220. So 0.4545 is a cos. So from this, what is sine phi? So is nothing but cos inverse of this and then apply sine to that. So sine of a cos of answer. Whatever answer I got, I just apply. So 0.89 is the cos inverse. So this is cos phi naught and sine phi naught. Once I have this, so simply I can find IW equal to I mu equal to. So this is I naught cos phi naught. This is I naught sine phi naught. So from this I'll get the working component of the current and the magnetizing component of the current. So let's do that. So 0.7 multiplied by 0.4545. So 0.318 amperes. So whereas the next one 89 0.623 amperes. So I got these two currents, and once I have this, now using the voltage I can find out the R naught. So R naught X naught equal to V naught by IW, and this is V naught by I mu. So that is V naught is 220, 0.318, and then this is 220 divided by 0.623. So let's do that. 220 divided by 0.318, 691.8. So I'll just write 692 ohms approximately, and 220 divided by 623. I'm getting 353.13. So I'm writing 353 ohms. So that's it. So using the short circuit test, so this is using SC test, sorry, open circuit test. So using OC test, I found two parameters. Now let's look at the short circuit test data. So 15 volts, 10 amperes and 85 watts. This is done on high voltage side. So if I denote this as the primary and this as secondary, so the values that I'll be getting will be R02 and X02. So first I have all this again. So what do you do now? How do we get? So 10 amperes and 85 watts. So from that I can find R01. That is I short circuit square into R02 is nothing but P short circuit. So 10 amperes into R02 is 85 watts. Is that correct? 85. And the short circuit current is 10 amperes on the high voltage side. So this 10 amperes is measured on high voltage side. So this implies that R02 is 0.85 ohms. Now let's calculate Z02. So Z02 is nothing but short circuit voltage divided by short circuit current. So short circuit voltage was 12 volts and short circuit current is 10 ohms. So I'll get 1.2 ohms as my impedance. So from this X02 I can calculate Z02 square minus R02 square under root. So that is square root of 1.2 square minus 0.85 square. So this will give me, so again 0.847 I am getting. So this will give me x02. Thus I have all the four parameters. So let's represent it in the equivalent circuit. So before I represent equivalent circuit, I have to refer everything to the primary side. So let's do that. So what is the K? So K is nothing but E2 by E1 or V2 by V1. So that is nothing but, so if I look at the data, so I have 400 and 220. So this is 400 by 220. So this is my K. So 400 by 220. 1.818. 1.8182 is my K. Now I want to find out what is R01. So that is nothing but R02 into K square, or is it divided by K square? So here again I don't have to remember it. Just look at this. K value is more than 1. So K square will be more than 1. And you look at the primary side is low voltage. So low voltage side will have lower impedance. So I have to divide by K square. So this is how I remember. So what is R02? 0.85 we have got it. So divided by K square. So that is nothing but, so K equal to answer. I am just storing this in answer. So 0.85 divided by K to the power of 2. 0.257. 0.257 ohms. Similarly, what is x01? Is nothing but x02 divided by K square. So that is nothing but 0.847 divided by K square. So let's calculate that. 0.847 divided by K square. I'm getting 0.256. That's it. I have all the values. Now let me just build the equivalent circuit. So equivalent circuit is like this. So this is the primary side and this is the secondary side. So this is V1 plus minus, and this is R01, which is 0.257 ohms, and X01, which is 0.256 ohms. So let me throw in J also there. Similarly, these values, this is X0. So how much did we get that? Going to the short circuit, 353 and 692. So this is 353 ohms and this is 692 ohms. This is R0. So this is the final circuit. So here I'll have V2 dash, which is nothing but E2 dash, nothing but E1. So that is what is there at this point. So I hope now you got something from this. Let's quickly look at one more problem, that is this one. So in the transformer, this is about separation of losses. In the transformer, core losses are found to be 50 watts at 40 hertz. So 50 watts at 40 hertz and 86 watts at 60 hertz at the same flux density. So when the maximum flux density is same, so what we know, hysteresis loss is proportional to A into F, and eddy current loss is proportional to B into F square. So this is what we know. So AF, so what we know is AF plus BF square equal to total losses WI. So A plus BF is nothing but WI by F is what we know. So from this we'll get two equations actually. So what is Wi? Wi is total iron loss, that is 50. So A plus B into 40 hertz is equal to 50 divided by 40. This is from the first example. Similarly, A plus B into 60 hertz is equal to 86 divided by 60. This is from the second test. So from these two equations, I can solve and find out the value of A and B. So let me just begin by subtracting these two. So if I subtract these two, so I'll get minus 20B equal to 50 by 40 minus 86 by 60. So let me do that now. So 50 divided by 40 minus 86 divided by 60. So this whole value, this whole divided by 20 will give me the value of B. So here also it's minus. So finally, I have to divide by minus 20 because there's a minus sign here. So 0.00916. So therefore B is 0.00916. So from this I can find what is A. So how to find what is A? So this is 50 by 40 minus B into 40. This is what is A. So that is nothing but 50 by 40 minus answer into 40. So A is 0.8833. 0.8833. Now what is asked in the question is what is the iron loss at 50 hertz. So I can now substitute for 50 hertz, that is A plus B into 50 equal to iron loss by 50. So therefore iron loss will be 0.8833 plus B, that is B is 0.00916 into 50, and this whole thing again I multiply by 50, so I'll get the answer. So let me do that. So 50 multiplied by 0.8833 plus 0.00916 into 50. So when I do this, so I'm getting 67 watts. So this is the final answer, 67 watts. So I'm able to at 50 hertz. I'm able to separate and then I'm able to find it. So this is another short problem. So let's do some more problems. Okay, so let's look at the next problem, that is example 33. And this problem is actually taken from example number 32.44 from the electrical technology by B.L. Tereja. So let's see this problem. You can also try solving this problem. Pause the video and then look at the data and then you can try solving this and you can match your answers with me. So let me begin my answer. So what I'll do is just look at this a little bit. You look at the what needs to be found out. I have to find an equivalent circuit referred to the primary side. Now, what is the primary side? So this is 450 volt side is the primary side, but the open circuit test is carried on the low voltage side. That means on the secondary side. So therefore, this R naught and X naught, if I calculate just by using this OC test results, will be on secondary side. So to avoid this, I will not use the actual OC test results. So we obtain or we simply transfer OC test results to HV side. that is primary, and then determine R naught and X naught. So such kind of delicate things you should be careful when the question is given. So let's do this. So why I am doing like this? It is easier to transfer the data and then calculate R naught X naught rather than transferring the impedances. Anyway, so let's begin. So see, 120 volts and 120 volts rated, it is matching. So therefore, if I transfer the open circuit voltage to the primary side, it will be 450 volts because of the ratio. So V open circuit on the primary side, so I'll put a dash, will be 450 volts. Now look at the current. So what is the current? 4.2 amperes. This 4.2 amperes, if I transfer to the primary side, so because the high voltage is there, the current will be less. So it should be divided. So let me just find the K. So K is nothing but V2 by V1. So that is 120 by 450, or nothing but 12 by 45. So based on this, I can find I open circuit dash is nothing but I open circuit multiplied by K. So that is nothing but what is the open circuit? 4.2 amperes, and then I multiplied by 12 by 45. So let's see how much I get it. So I am going to calculator. 4.2 multiplied by 12 divided by 45. So 1.12 amperes. So I have the short circuit current. Now coming to the power, so power is power, whether it is on the secondary side or primary side, it is essentially measuring the core transformer losses. So therefore the power will remain same. So power in open circuit is 80 watts only. So now I can find R naught. So before I find R naught, so what I should do? First I should find the cos of phi naught. So cos of phi naught is P open circuit divided by V open circuit, I open circuit. I'm just keeping these dashes to be consistent. So this is 80 divided by 450 multiplied by 1.12. So what is that? So let's calculate. 80 divided by 450 multiplied by 1.12. 0.1587. So I'll just keep it as 0.159. So this is 0.159 ohms. So this is cos, I'm sorry, not ohms. This is cos of phi naught. So therefore, from this, I can find out what is my IW and I mu. So IW is I naught cos of phi naught. So I naught means that IOC that I have to use. So 1.12 into 0.159, and then IOC dash sine of phi naught. So 1.12 into sine of cos inverse of 0.159. So using these two, I'll get these two currents. So let me do that. 1.12 multiplied by 0.159 is 0.178. 0.178. So this is amperes. Similarly, sine A cos. I'm just finding cos inverse and multiplying. So this is 1.1. So I'll just approximate it to 1.1. So now that I have these two, so I can find R naught, which is nothing but V naught by IW. This is nothing but 450 divided by 0.178, and X naught is nothing but V naught by I mu. So that is nothing but 450 divided by 1.1. So let's do this. 450 divided by 0.178 and 450 divided by 1.1. So I'm getting 2528 and 409. So let me write that 2528 ohms and 409 ohms. So these are all referred to primary. So that's good. Now let's look at the short circuit data. So when I look at the short circuit data, I have short circuit. So this is meters are already connected in high voltage side. So high voltage side is 450 kV. So I'm already on the HV side. So first thing you verify whether this 22.2 amperes is actually short circuit current. How do you verify? 10 kVA and 450. So what will be the full load current? So 10 kVA divided by 450 V. So that is what, let's do 10 divided by 450. So since it is kVA, I will multiply by 1000. So I'm getting 22.22. So the test is good. So I can use the data. This is just a verification. To verify that see what is the other verification? For the open circuit test, you verify whether the voltage is rated or not. For the short circuit test, you verify whether current is rated or not. Anyway, that is done. So I have these three readings. So from three readings, what we can find? So I can find R naught 1, so 22.2 and 120 watts. So so ISC square R naught 1 equal to PSC. So this implies that R naught 1 is equal to, so short circuit power is how much? 120 watts. Okay. So this is 120 watts divided by 22.22 square. So that is nothing but 120 divided by 22.22 to the power of 2. So I'm getting 0.243. So that is my R01, 0.243 ohms. Next, let me find Z01. So this is nothing but the short circuit impedance. Nothing but voltage of short circuit divided by current of short circuit. This voltage is given to be 9.65. That is typically expected. Voltage will be somewhat less voltage, 9.65 divided by 22.22. Let's see how much we get it. 9.65 divided by 22.22. I'm getting 0.434. Let me write that. 0.434. So from these two values, now I can find out x01. Nothing but z01 square minus r01 square. So square root of 0.4343 square minus, and r01 is found to be 0.243. 0.243 square. So 0.36 is my answer. So here I am getting x01 is 0.36 ohms. So I can always put a J to indicate it is reactive. So I found these two values, and now I can make an equivalent circuit. So I have R01, X01, R0 and X0, everything. So if I make an equivalent circuit, so it will be something like this. So this is R, this is X, this is again R and X. So this is 0.43, I'm sorry, this is 0.243 plus J 0.36. This is primary. So this is the supply voltage V1. This is 450 volts. This is R0, which is 2528 ohms. 2528 ohms. And this is X0, which is 409 ohms with a J. So this is my equivalent circuit for the system. So there still the problem is not over. I have just done up to here. So we will continue and do the rest of the problem. Efficiency and voltage regulation calculation. let's continue with part B of this question, that is efficiency and voltage regulation. So first let's calculate the voltage regulation at power factor of zero point 0.8. So what is the voltage regulation? So for that, first we should, this is part B. So first we should find out what is the voltage drop. So rated current at full load is, we already know, 22.2 amperes here. So therefore from this I can just find out the voltage drop, nothing but I R01 cos phi naught phi 1, actually phi 2, this is I1 dash, plus y plus, because the power factor is lagging, so I1 dash x naught 1 sine of phi 2. So this is what we have to do. So already R01 x naught 1 we have, so I just have to do this. So I1 also I know, so 22.2 I'll just take as common. So R01 is 0.243 multiplied by 0.8 power factor, plus already taken common, so 0.36. So here are the values. So into 0.6. So this is my voltage drop. Let's do that. So I go to the calculator. 22.22 multiplied by, okay, 0.243 into 0.8 plus 0.36 into 0.6, 0.36 into 0.6. So I'm getting 9.12 volts as the drop. So I'll write that here, 9.12 volts as the drop. If this is the drop, then what is the voltage regulation? It's nothing but voltage drop by rated voltage. We are doing everything at the primary side, so I'll keep V1. So 9.12 divided by 450. So I multiply by 100 to get it in percentage. So 9.12 divided by 450 into 100. So I get 2.0267 percentage. So 2.026 percentage. So this is the percentage regulation. Now coming to efficiency. So for efficiency, first of all I should know losses. So losses, the good thing is, because this is all losses at the full load, whatever the test we have done, that itself will tell me. So copper loss is 120 watts under short circuit, and iron loss is 80 watts. So the losses I know from AC test and OC test at full load. So that is 80 watts plus 120 watts. So that is 200 watts. And what is the output? So output, it is mentioned that full load at 0.8 power factor. So what is the full load rating of this machine? So if I again just check it once again. So here 10 kVA is the rating of the machine that is given here. So if the 10 kVA is the rating, so 10 kVA multiplied by 0.8, so will give me 8 kilowatts as the output. So therefore efficiency is 8 kilowatt, that means 8000 divided by 8000 plus 200. So output by output plus losses. So let's do that. Divided by 8200. So 97.56% is the efficiency. So I got the efficiency also. Now let's take the part C of the question. So now if I go up, part C, what it is saying, efficiency and voltage regulation for half load at 0.8 power factor leading. So at half load, the current will be half. So therefore, so the current will be only 11.11. That is half of the current. And then what is R01? R01 is 0.243 multiplied by power factor is 0.8. Here I have to use a minus sign because the power, it is leading. The load is leading. And then what is X0? X0 is 0.36. So 0.36 multiplied by sine phi naught. So if cos is 0.8, sine will be 0.6. So this is my voltage drop under half load. So let's see what will happen. So I just go to the previous formula. Here I replace with minus, and then here I'll replace with 11.11. So I'm getting the value has to be negative, which is expected. So minus 0.24 I'm getting. So minus 0.24. Very negligible amount of voltage. Voltage drop is actually positive. So now percentage regulation will be minus 0.24 divided by 450. So into 100 for getting into percentage. So I'll get minus 0.24 into 100 divided by 450. So I'm getting this as a percentage, minus 0.05%. Minus 0.053% is the regulation. Okay, regulation is done. Now let's calculate the losses. Losses, actually what happens at half load, the copper losses, so at half load, current is half, therefore current is half, therefore copper loss is 1/4 because it's a function of square of the current. So therefore it is 1/4. So therefore losses 80 watts iron loss will remain same, and then 1 by 2 square multiplied by 120 watts will be the copper loss. So this will be 80 and this is 1 by 4, so it will be 30. 80 plus 30 will be 110 watts. So this is the total loss at the half load. And at the full load, the output power was 8 kilowatts. So we, as we did in the previous here, 8 kilowatt. So at half load 0.8 power factor, the output will be half of that. That is 4 kilowatt. So that will be 10 kVA multiplied by half multiplied by power factor 0.8. So that will be 4000 watts. So I know the losses and this one. So therefore efficiency is 4000 divided by 4000 plus 110. So this will be 4000 divided by 4110. 97.32%. So slightly reduced the efficiency. 97.32% is the efficiency. So I hope you learned something by solving this problem. Let's look at one more problem. Question. And then another thing is, if you refer, like here what is given, R01, X01 values and are given. So if you refer back to our earlier question number 31, so OC test and SC test results were given, and finally the output I got is this one. So what I have done, this 257.256, 692 and 353. So these parameters I have now given here, 257, 256, 692 and 353 ohms. And given these parameters, what would be the test results? We want to do the reverse thing. So let's get started. So you can try yourself to solve this, and then you can match your answers with me as usual. So i'm I'm just trying my solution. So let's see now. Look at the this one, R naught and X naught, and the open circuit test is usually conducted at the low voltage side. So already this is in primary 220 volts. The meters are at 220 volts. So I can use them directly, which is a good news. So let's do that. So how do we get this working component of current? So working component of current, I will get it if I multiply open circuit voltage, like if I divide open circuit voltage by R naught. So this is what we know. So open circuit voltage has to be 220 volts. So 220 volts divided by R not given, that is 692. So this will be my answer. So I have calculated this, it is 0.318 amperes. Similarly, the I mu will be open circuit by X naught. So that is nothing but 220 divided by 353, and this also I have pre-calculated, 623 amperes. Now that I have IW and I mu, so from this I can calculate I naught. So I naught will be IW square plus I mu square under root. This also I had pre-calculated. I am getting zero point 0.7 amperes. You can actually do it yourself. I am doing with pre-calculated values to save some time. Now, what is this power? So the power is nothing but whatever loss is there in the this one. So IW square, whatever loss is there in the R naught. This is nothing but the iron loss. So what is IW square? So 0.318 square multiplied by 692. So this will be my losses. So this I am getting 70 watts. So therefore, finally my open circuit test, if I perform, so I'll get the voltage will be 220 volts and the current will be 0.7 amperes and the power will be 70 watts. So this is what will be my open circuit test results I am expecting. Now let's look at short circuit test. So which I will write here, whatever the solutions expected. So in short circuit test, again, it is what we have to do is here R01 and X01 are referring to the primary side, but the short circuit test uh, the will be conducted on the secondary side. Therefore, I have to transform this to the secondary side. So what is my K? So K is 400 by 220. So this is my K, or 40 by 22, or let's say 20 by 11. So this is my K, and then R01 transfer to the secondary side. Therefore R02 will be K square into R01. That will be 20 by 11 square into R01. So this I will be getting some value. Similarly, X02, that will be again K square into X01. So 20 by 11 square into X01. So I'll be getting these two values. Once I have these two values, then I can calculate the uh, I can calculate the expected results of the short circuit test. So let's do this quickly. So let me go to the calculator. So I have K equal to 20 by 11. So therefore, what is R01? R01 is 0.257 multiplied by K square. So this is 0.85. Similarly, this is 256 multiplied by K square. This is also 0.846. So I'll just, in the best interest of time, I'll just write 0.85 and 0.846. So I have these two. So then what is Z02? So Z02 will be 0.85 square plus 0.846 square and then square root of that. So square root of the answer 1.4382. So 1.12 I am getting. So this is Z02, that is 1.12. So now that I have this, so what is the short circuit current? I short circuit current will be the rating 4 kVA, so divided by 400 volts. So that is 10 amperes. So therefore, V open circuit, V short circuit will be multiplication of these two. So 11.2 volts is expected. And then P short circuit will be 11.2, that is 10 square into this resistance 885. So that will be 85 watts. So I think this is 85, 11 and 10. So this is 11.2 volts, 10 amperes and then 85 watts. This is matching with the solution.